Hello and welcome everyone to episode 13 of Talking Shop with Tony Abbey. My name's David Quinn, Chief Marketing Officer at NAFEMS, and I'll be your host for today. This week, Tony's asking the question, FE models under or over constrained? We'll kick off with a 30-minute presentation, then open things up to your own questions and comments. So without wasting any more time, I'll hand over to Tony.
Thank you very much, David, and welcome everybody to episode 13. FEA models, are they under or over constrained? A recent pub discussion with ex-colleagues, you recognize most of them here, and basically this was taken before the COVID outbreak, so we haven't done any social distancing. And basically the conversation went something like, what's the most common error you make in FEA models? And actually this often happens. I go to conferences and so on, have a few beers with colleagues and so on, and often the answer is in the chat, just forgetting to properly constrain or to ground the model. So of the over-constrained, under-constrained, that's going to be definitely an under-constrained model. We just forget in some way to do that. It's very, very easy to kind of make that mistake. About every 4 or 5 models I run, try and run it as static analysis, it just fails. It just falls over because basically it's not properly grounded. Here's rigid body modes. I've forgotten what was this guy's name?
Stewie. That's
Stewie.
Sorry. It depends, so Stewie or Stewie.
Stewie, okay, we'll call him Stewie. So he's found a rigid body mode, and the reason here is we've got dissimilar elements, and there's only the translational degrees of freedom connected, so we get a rotational rigid body mode. Very, very easy to do, and I think most people have probably done that at least once in their career, probably much more than that as we go through. So rigid body modes, they're often due to inadequate constraints. And in many ways, it doesn't seem fair. Stewie is here still saying, gosh, rigid body modes. If we look at a load diagram, we've got a force coming down on this little simple beam. We've got rollers supporting it. So put P in the middle, P over 2 reactions both sides. I can see that load path. I can sketch the load path. Why on earth does FE analysis not understand what it is I'm trying to do? And this is, I think, the major source of frustration. The loads I'm applying in balance, I can see my reaction paths. The trouble is FEA is being really, really kind of picky and pedantic in saying, okay, we've got load balance, but we've got inadequate constraints. So it's actually assembling the system stiffness matrix, then partitioning out the constrained degrees of freedom, is looking at that matrix to invert it. That's the mathematical explanation. So it doesn't actually care about the loads. If you put the loads on in balance or not, it's not actually put the load set on at that point. It's just looking at the conditioning of that matrix. So in another way, more physical kind of way, you could say, well, it's searching for any possible rigid body mode. So if I were to put a load coming from the left, then yes, now I've got something which is not a static solution, it's a dynamic solution. Force equals mass times acceleration. So unfortunately, we have to come to these to the right-hand little diagram there, and we put that constraint, which is like a lateral constraint I've tried to indicate there, even though it's nothing to do with the particular load path I'm interested in at the time. There's me, maybe a week later, maybe somebody else picking up the model. This model could say, let's put a load on going from left to right, and then we get caught out. So that's the frustration, is like, doesn't FEA get what I'm trying to do? I put these loads on, everything's in balance. I see that. Why doesn't FEA see that? Well, it's just the nature of the beast. It's just a mathematical process. It's looking for that matrix to see if it's conditioned properly. So I think that's this misunderstanding of the intention of the load path and what FEA is trying to do is probably the main reason there. And I am incredibly guilty of this. Very often a model I set up has this kind of issue. On the Intro to FEA course, we kind of go through in some detail. Here's a brick element. I assume it's grounded. And here we've got dissimilar elements. The brick element only has the translational degrees of freedom. So it has the 3 translations T1 through T3. The bar running in has all 6 degrees of freedom at the end. So when we assemble that stiffness matrix, assemble the degrees of freedom, stiffness terms associated with, let's say, grid 99, which I've kind of sketched in here, the system can't cleanly remove degrees of freedom. All the other corner nodes for the brick element can say, well, there's only translational degrees of freedom. no rotational degrees of freedom, no stiffness terms, so we could just eliminate those from the problem automatically. But grid 99 becomes a problem because we can't eliminate it, so it means there's no connectivity as we come down in here between stiffnesses of the rotational stiffness of the bar, and there are none of the brick element. So we get actually 3 rigid body motions there. So it's an unsuccessful result. We're going to get rigid body motions, and away we go. So there are many and varied reasons why we can have it. Forgetting to constrain a model, dissimilar elements, and so on. Here's another example of dissimilar elements, and this one actually embarrassed me because I set this up again as a little benchmark for the Intro to FEA class. And I thought, well, the idea is we've got a very solid stiff section here. It doesn't lend itself to thin wall idealization or shell idealization. The green on the left, the green on the right, and there's a very thin section in between. So sideways view looks something like that. But well, I set that up. I set up a pinned edge, apply a pressure load, and that will demonstrate the problem. Well, again, this is classic. I forgot that there's actually 0 stiffness axially developed, out of plane developed through here. So it actually becomes a three bar linkage. So it's a kinematic problem, not a structural problem. And I just couldn't see it. So I had to run a normal modes analysis, which is our usual thing to say, well, show me the rigid body modes, because static analysis won't. And here is the first 2 rigid body modes, 2 mechanisms in here, the 2 pivot points. And this is a classic way of I just couldn't see it. And very often that's the situation. I can remember doing a galley structure for Boeing many years ago, and the galley structure seemed to have a nice set of constraints. I followed everything, but actually the whole thing was free to spin around, and it took me a little while to figure out what was going on there. So it's not always trivial figuring this out. Now, many of you may say, well, I always find it easy. Okay, then you're a better analyst than me. That's all I can say. I fall into this trap from time to time. So we got a wide range of constraints. I just couldn't resist this. I went mad with the Google images. So we've got Stewie here with his rigid body modes, definitely under constrained. We can't even solve it with statics. And then there's this phenomenon called over constrained. We're gripping something, holding it to ground, and maybe all over the place, and we can call that over constrained. We'll have a look at that. And then we've got this minimum constraint. We're actually literally spinning plates so that we just keep our model kind of from falling over, just like the spinning guy. I was trying to find a spinning guy with 6 plates, which would be 6 degrees of freedom. But I guess that would be, you'd need to have his feet, his head, or whatever. So anyway, we've got 3 there. But so that's the kind of range that we can have. We're going to have a look at this range. We looked at under constrained, essentially rigid body modes coming in. The structure won't run statically. Over constrained is more subtle. Is the model over constrained or not? There's an issue we can kind of talk about. And then the minimum constraint is a very interesting kind of approach. It actually becomes a particular methodology we can have a look at. So over constrained models, we often get this on YouTube, like, what's up guys, I'm going to show you how to do an analysis of something. So here's a Conrod, and we're going to apply a load at the big end, and a nice, say, bearing distributional load. How are we going to constrain that? Well, let's just build the left-hand end in. So where are the stresses viable? Well, clearly they're not viable. They don't make any physical sense in this area down in here. So we've got the issue that in a particular case, the stresses to the right are okay, but to the left they're meaningless. And remember St. Venant's theorem? I think that was one of the very early talks we had. So the stress distribution, as it comes out, say, about 1 diameter, is probably okay up to this point. But then the stresses are just frozen out at this particular point here. So it's not a good way to do an analysis, but it's quite a common thing to do. Another issue is that we've got here another setup. We've got across an I-beam running down in here. Now it's supported at the ends. So we've got some kind of cross member which is built in at the red lines here. There's a distributed line road running down the back in here. And often we don't want to do a full assembly, want to kind of simplify things. So is it reasonable to assume the I-beam is built in at both ends? So like the guerrilla approach would just be to say, well, we've got structure here, let's just build it in here, build it in here. Is that a reasonable approach to take? Well, if we actually look at that, it depends on the stiffness at the boundary. And I've had great fun going through a range of different, I just use beam elements, it's very easy to set up. This is the guerrilla approach, which is saying that we're going to build in at that end and build at that end. This is the bending moment diagram, and it's showing if we go from like minus 30,000 root bending moment here, the root bending moment is the maximum bending moment, and then we're getting something a little bit less than that, so about 20,000 in the middle there. That, due to the distributed load, is the bending moment, and the bending stresses follow. So the critical region here is going to be the roots, and maybe we get some relief in the middle. As we actually drop that torsional stiffness, here it's infinite. Imagine a rotational stiffness here. It's infinite. Remember, these are cross members, so I can talk about the rotational stiffness of this little channel in here. Here, with built-in, it's effectively infinite. Here's a really big, thick, chunky structure, and its torsional stiffness is very high. You can see it's a transition, and we're getting less root bending moment because there is some compliance, some flexibility. The center bending moment is increasing, and if I go all the way down and end up with a fairly lightweight channel over here, the torsional constant has dropped down tremendously. Now we're actually very close to the pin supported point in here. So the root bending moment, it barely exists. There's very little resistance here. Now the center bending moment is really the critical section. So if we're designing, we're thinking about how to design this. If we actually have a very flexible member, and it's the torsional stiffness which is supporting, then this guerrilla type over-constrained approach is wrong. In the aircraft industry, we used to have a lot of problems with, like, for example, spars, the root spar coming into the fuselage. Well, the fuselage is going to grab hold of that root spar fitting, and it's going to build it into ground. We get the same kind of effect. You get the wrong bending moment distribution due to that end fixity. So the guerrilla type approach, over-constraining, we need to think quite carefully about that. Now, this is perhaps a trivial example. It's more of a demo example. But it is quite subtle. Is the model over-constrained or not? Now, talking of over-constraining, this is what I call the scuba tank conundrum. I've got a scuba tank here which is under equilibrium in internal pressure, and it could be in water on somebody's back, it could be standing on the dock, whatever we want. But it's pressurized. It's got an end cap on it, and so we have the hoop stress, we have the axial stress, and the through thickness radial stress. And they're all in balance. So we can't run that, though, within FE analysis. We've got to have some constraint. If we don't put any constraint, we've got 6 rigid body motions. It won't run statically. So how do we get that constraint in? And by definition, any kind of constraint I apply to it is going to be over-constrained. Here I've got some helpers trying to help me out. So this guy's welded the scuba tank to some sort of base. Well, again, the pressures in the nozzle region, stresses, in the nozzle region, probably okay. But down in here in the base, I've completely messed up the stress distribution. These guys are trying to put some sort of handle on it to sort of say, well, we can constrain it. In the aircraft industry, we used to call these like sky hooks. Something comes down from the sky, tries to grab hold of the aircraft structure and stops it kind of moving around with rigid body motions. Anytime I do that, I'm going to put local stress disturbances on. So the constraints are disturbing just the natural balance of that. So we can't just apply zero constraints. How can we constrain it? Anything we do could be very contrived, not realistic, introducing local stresses. So for many years, this was an issue. And if I go back to what was Hawker Siddeley Hatfield very proudly, and then became part of BAE, and I was working there in the late 80s. And we had 3 aircraft projects going through, the 146, the 125, and the A300. We just started to join up with Airbus. So the question was, This is a free-flying model. Obviously, it's a little bit like the scuba tank. We've got weight, we've got lift, we've got force, thrust, we've got drag. Well, in fact, all 6 degrees of freedom in flight are balanced out for just steady, let's say, level flight. So how do we do an overall FEA model, which we had overall loads of models? How do we balance these? And this is where the skyhooks came in and special techniques. And we had 3 chief stressmen on the 3 projects. And FEA wasn't very common then. I was doing the FEA model of the 125, a kind of retrofit model. And the question was always, well, how are we putting this FEA model into balance? This is a quick shot of the Comet motel, basically a pub. And on a Friday lunchtime, it was, you wanted to cause a little bit of a discussion, you just get hold of the, say, chief project engineers on a couple of these, or the chief stressman if they're around, and say, can you tell me again how you're holding your model in equilibrium? And in fact, there were 3 different philosophies, as in many cases with FEA, across these 3 different projects. So discussing that over a few pints was very interesting to see how it was actually achieved, how we got that not over constraining. If you grab hold of this aircraft somehow, grab hold of the center section, apply the load balance to that, you've over constrained the model. You've not got natural constraints in there. So there's a bit of an issue there. Think of the Conrod here. We had a picture before. We had the was up guys. Let's ground that and apply the load here. So here we've got a load case where we are applying a load condition A and then constraining at the end in here. So that's what we're representing. Or we could say, well, we really want to know the stresses at the little end, so let's turn it around. Let's constrain in this end and a load here. Now, we don't really want to do A or B because we get poor local stresses, the model is over-constrained. And also, every time we do this, we're changing the boundary conditions, we're changing the stiffness matrix, so it means a new FEA model. I'd like to set up C, which is just basically nicely in balance, where is it action or reaction is actually a little bit of a philosophical argument. We could say, well, it's either we think of it as a reaction coming at the crankshaft here, or it's an applied load coming from the crankshaft. One man's reaction is another man's applied load kind of thing. So this is what we'd like to do. We'd like to do condition C, and we'd like to do lots of them depending on the particular inertial load state, or let's say part of it as we go through the complete 720 power cycle of a Conrod. We'd like to do these as not different models, but different load cases. And you can actually do this. There's a method called the minimum constraint method, and for those of you not familiar with it, it's called the 3-2-1 method. And you might want to try that. Just get a block, mesh it. We need a coplanar set of 3 nodes. So here's the first node, and I'm just going to constrain that corner in the translation. There's 3 translations. That gets rid of, obviously, of the 6 possible rigid body modes. I just got rid of 3 of them. Now we shoot down the red axis and we come to some point in here, we intersect that node. If I constrained in the red direction, which is X, I'd lock in strain down in that length. I don't want to do that. So I'm going to put 2 constraints at right angles to that vector, so the green and the red. Now I've stopped spin about Z, the 2 greens. I've stopped spin about the green. That's the 2 blacks, but I'm still free to spin about the x-axis. So I have one last constraint to apply, which is again we shoot off here at right angles and constrain that in the y direction. That stops that last spin about the red axis. So that 3 constraint, 2 constraint, 1 constraint, hence the term 3-2-1, that will actually, that's the minimum set of constraints. We've got 6 rigid body modes, we applied 6 constraints, so that then we're in business. And if we apply equal loads, and here I put pressure on one side, pressure on the other side, then I just get a constant stress state in here. Now the key thing here in this particular methodology is you've got to apply perfectly balanced loads. If I apply just load on one side, then I'd be ripping against these point constraints. And we already talked about singularities. I'd actually have a whole bunch of singularities in the model. So it has to be in equilibrium. We do get the reactions out. They are viable reactions. We're not cheating anyway, but the reactions are so tiny that they don't introduce any local stresses around there due to the reaction. So it's called the 3-2-1 method. Give it a try. If you don't remember the recipe, just send me an email. I'll happily kind of send you this kind of screenshot. It's very, very useful kind of approach. So here's now my Conrod. The loads must be in balance. So the pressure distribution at that end, or the bearing at that end, the big end or the little end, they must perfectly balance. Then I put a cut plane in here, and on the cut plane I've got 3 vertices. There's my 3, 2, 1. We follow that recipe, and then this is the FEA result. I do have tiny little reaction forces in those cut regions, but they're so tiny there's no evidence of any stress reacting there. So now I've got my kind of cake and eat it. I've got the big end, real good stresses. I've got the little end, good stresses. So I've achieved what I want with this minimum constraint method. So it's a very powerful, very, very useful method. Here's a slightly more complicated example. I've got some kind of actuating rod pulling on here on this. It's like a lever arm. It's like a gripping arm. It's pivoting about a pin here, and the idea is to squeeze something in here. So I can set that up in as a minimum constraint, and I can say, well, the target is to put a particular squeeze level in here. It'd be a force which would turn into a pressure distribution. These would become bearing distributions. So with that, I can set up a free body diagram and solve it. So I also put my minimum constraint set on. Here I've chosen that particular face. I could have chosen that set, put a slicer anywhere to give me three coplanar points. We'll create nodes and do my 3, 2, 1 through them. So here's my set of load cases. I want to set up all these load cases in one analysis. So I want to actually see the result of the different crank angle. I'm changing the crank angle around, keeping a constant resistance in here. With a little spreadsheet, I can come out with what that magnitude is of each of these, the reaction there, and the vector associated with that. So that's fairly straightforward to set up in Excel. And I can batch these now as subcases up, or load cases, with the same constraint. So I'm not changing the model at all, and that's pretty powerful. The bearing setup is very convenient. If I know the line of action, most preprocessors now, I can just paint the whole of this inside surface, say that I've got a sine distribution over that 180 degrees. So I don't have to pick off the right elements or anything. It just says, well, okay, whatever the vector is, it's 180 degrees, I'll figure it out, which is very powerful. So we can actually turn that free body diagram into a pressure distribution using a very reasonable engineering judgment call on that bearing distribution. So for things such as I've done Conrods under the full power cycles, things like that, it becomes very, very useful. So if we look at the results now, this is just a 0-degree angle. We're pulling here. There's the reaction here. And then we're actually changing that crank angle around. So I've just shown it. It's come to the extreme end here. We're pulling the crank angle this way. We're squeezing here. And there's a transition in stress state. But again, we're not changing the model. We're just changing the load case. So you can actually animate through here, which is kind of fun. And you can see here, for example, this is predominantly like a cantilever bending with stress concentrations around the hole here. Similar kind of cantilever bending here, but now we're getting a very big compressive load building up because we've got a mechanical disadvantage coming up in here. So we get a big compressive loading in there. So that change in state very nicely shown with just one model, a whole bunch of different load cases. So big advantage, many advantages in there. Now, one of the problems with the 3-2-1 model is that we've set a datum set of translations. So the 3 position, which is on the corner here, that locks in the translations. So any displacement is relative to that point. And I've had clients kind of say to me, well, it's not right because the crank is wanting to pivot about that point. Well, there's a useful little technique there. Remember the spiders we talked about? We had Spider-Man the other week. I can put a flexible spider in there, which adds no stiffness to the structure at all. It gives me a datum point in there. And many post-processors, we can actually say, plot me the deformations relative to that datum point. Now we see something sensible. We see the crank pulling around here, squeezing up here. It's the same deformation, but now it's relative to the base point here rather than to this point in here. So we can easily overcome that. Neat use of the flexible spider there. The other thing is sometimes the free body diagram, it's fairly easy in that particular case, the crank, but sometimes it's tough to figure out. So what I can do is, again, with my known pressure distribution, I've got a known crank angle in here. Another way I can approach this is to slip in now my rigid spiders. Isn't it funny how spiders coming back to haunt us? And basically the crank in here, the pin, I want to resist horizontally and vertically. We also have to deal with outer plane. I haven't shown that in this particular case. And then I just have one line of action of the actuator. Set up a local coordinate system here. I've got a constraint in a rigid spider to ground here, aligned in that direction. I've got a constraint in my global coordinate system and that rigid spider. What comes out is the reaction forces. Now, the stresses are junk. They're not interested in those. What I'm going to grab is these reaction forces and put those back in as applied loads. So I'll take those reaction forces and then say, let's put them back in as these loading actions in here. So quite complicated 3D load balance where it just defeats me how to do it. I can actually use the rigid spider to say, let's use FEA to do the free body diagram calculation for us. It can calculate the unknowns if I set it up like that. Again, useful application on the rigid spider. I stress then we throw away the rigid spiders. We just apply the loads that we've developed or the reactions back as applied loads. So a neat, to me that was a bit of a breakthrough with some very complicated models, trying to figure out in 6 dimension or 6 coordinate, well, the 6 degrees of freedom, what the load balance is was tricky. But again, FEA can help us out there. So we've got this 3-2-1 method, which is a minimum constraint method. An alternative, and many people have asked me about this, is inertia relief. Inertia relief works in a different way. What it does is to say these are the total loads applied to my model. If I've got out of balance loads, in that particular case, like I don't apply any constraints at all, then it's going to say, well, let's say I've got an out of balance load, let's say. The out of balance load is going to be resisted by an inertia reaction distributed through the structure. So we get distributed body inertia forces. Basically, we've got an out of balance force, and then we're going to balance that by force equals mass times acceleration, where the mass is going to be the distributed mass throughout the structure, and the net acceleration is going to be calculated. So we have a resisting inertia force being developed automatically. The rigid body motion is suppressed by eliminating rigid body modes from the system matrices. The way it does it is a little bit more mathematical, and we can either say let the system do that automatically, so it's going to figure out a way to eliminate rigid body modes by just basically not setting up reactions, but just partitioning out those degrees of freedom from the model. And it assumes, again, the model is in perfect balance. Now, there can be some unforeseen side effects there. What you can do is actually automatically define those 6 degrees of freedom which partitions out the rigid body modes. They're, again, not putting in reactions. They're just a way of partitioning out. That's actually directly analogous to the 3-2-1 method, so I prefer to use that if possible. Now, if there's no out of balance, then there's no distributed body forces. So what it does is I have a load in equals load out. It says, well, okay, I will allow that sort of like that magic, no constraints, but there's no inertial load distributed in there. So that would be an alternative to the 3-2-1 method. If there is an out of balance force in there, it's best to use that approach when that out of balance force represents a real inertial loading. And I'll have some examples of that coming up very shortly. If you don't, then you're saying, okay, my out of balance forces, somehow they're balanced by inertial loading, and it can become a meaningless type of loading. I'll show an example of that coming up a little bit later on. So we can't just use it to fix up a model. We want to be thinking about inertial relief. Either we're in balance, equivalent to 3-2-1 method, so there's zero inertial loads, or we have genuinely resisting with an inertia resistance to a structure. So don't sort of use it just as, I've seen people use it just as a kind of a band-aid or a fix-up. What do the inertial loads mean? Well, they don't actually mean anything. So here's the Conrod again. The loads are applied in balance as before, but now I'm not applying a constraint set. I'm just saying to the system, and in this particular solver I can say, you figure out the automatic inertial relief, and then essentially it's going to do partitioning out rigid body modes and then put the remaining structure in balance. And this is, we get actually stress results identical to the 3-2-1 method. There's no inertia contribution in here because there's no net force balance. There's no force equals mass times acceleration being developed in the structure. So it's an equivalent system, an equivalent approach. It's actually not quite, if this automatic, this is a displacement field, and I don't quite get a zero in, hard zero, and the actual deformation is sometimes a little bit problematic. That's sometimes the issue in there. Because we are constraining out essentially rigid body modes, it's not done in quite an orthogonal, a neat orthogonal set of degrees of freedom. What we can do is put in user-defined support systems in here. Again, they're not reaction points. They're basically saying those are the degrees of freedom we're going to partition out. And then we get identical displacement result and stress result. So those two systems, using a user-defined support system, using the same principle as the 3-2-1 method, we get exactly the same results out. So why use the 3-2-1, use inertial relief? Well, let's say we've got the Conrod coming in now. We've got the piston at the little end and the big end reacting at the crank. Well, the load path is going to be, the piston's going to be flinging itself out with, say, 5,000 pound force. That's going to be reacted at the big end. But then we've got the inertia contribution of, let's say, centrifugal acceleration of the Conrod itself. It develops a body inertia load. And if I say that body inertia load is 2,000 pound force, which is basically the mass of the Conrod, whatever it might be, times the centrifugal acceleration, Newton's second law, force equals mass times acceleration, I've got an outer balance at the big end reacted by the inertia contribution coming from the Conrod. And this is the right way to use inertial relief. There's a justification. We're trying to say not just the static load of the piston reacting against the crank, but also the additional load, which is the body load due to the Conrod whirling around there. So if I do that, then we actually have, now inertial relief is really playing its role. It's saying the outer balance force is being balanced by the inertial load in the Conrod. So we get bigger stresses at the big end, and I've compared it here to something in balance. In other words, no inertial load and inertial load. You can see that the effect is to build up a load, obviously at this end, build up the stresses. The stresses are bigger here than here. At the little end, it's very similar. Basically, it's just a distributed inertial load in here, and it doesn't do very much to the local stresses kind of in there. Let's actually switch off or look at the inertial load on its own. So in this particular case, I've just got an imbalance. So I'm saying, and the crank, the big end is reacting against the crank, and it's basically a crankshaft, and that's the reaction. Well, what's the application? Inertial relief is going to say, well, there's an outer balance 2,000 going to the left. That is going to be set up at all the little elements in here. They're all going to have their mass. Force equals mass times acceleration. It's going to figure out an inertial load which balances that. So think of this as a body inertial load distributed through. The big effect is at this end. The stress is just to inertia, which is distributed through here, of actually very small at the little end. So this is just a body inertia load resisting this, resisting against the crank here. So the key thing is there's no hard reaction path through here. The stresses in here are just kind of all of that lot is acting as a body reacting against the crank in here through the little end. And that's the point I was making. If you just use this to kind of fix up a load, say, here's the load applied here, I don't know, put it in balance. Well, what does it represent? It's this kind of smeared body load. If it does represent genuine inertial loading, then we're in good shape. Otherwise, again, it's a bit of a nonsense. So just be careful about how you use inertial relief. There's a lot more to inertial relief, but this is kind of just skimming the surface of it. So inertial relief and the 3-2-1 method are the minimum constraints methods. So kind of in conclusion, boundary conditions are probably one of the most difficult aspects in FEA. To try and simulate them properly, what's going on in the real world, what are the real boundary conditions, very, very tricky to do. And I think that's probably the failing of a lot of FEA models, certainly mine. It's easy to forget to apply the adequate constraints, rigid body modes. In many ways, under-constraining is perhaps the most obvious mistake. We see it won't run. We switch to a normal mode analysis to figure out what's going on. Over-constraining is more subtle. Now, this guy doesn't look very subtle, but basically, you don't always realize you've over-constrained a model. We had the beam there. We had the too much constraint is applied. The structure is not compliant enough. It wants to be able to respond in a more natural, unconstrained way. So over-constraining is subtle. We need to look very carefully at the physics of the boundary condition to make sure we got it right. That contrasting, for example, torsional stiffness of my cross members, is it fully built in? Is it simply supported? Those are the extremes. Somewhere in the middle is where we're actually going to be. Now, the minimum constraint method or inertial relief method is attractive because it actually avoids constraints. We take the decision there that instead of trying to constrain to ground, take load out, we're going to say those reactions, we're going to apply them back as actions. And it's a little bit philosophical, really. Is it an action or is it a reaction? It's just really your point of view. One man's reactions, another man's actions kind of thing. So we can actually put as a load balance, we can call it either an action or a reaction. The avoiding constraints, though, is actually avoiding over-constraining, a kind of grounding out. We do miss any stiffening effect of bearings, of pins in bearings and so on, but I think that's secondary compared to the danger of over-constraining. So I think the minimum constraint method helps us with our over-constraining issue there. Now, an alternative to putting minimum constraint method in would be to put in boundary stiffness. For example, on my beams, that I-beam, at the end, I could have actually figured out the torsional stiffness, turn that into an equivalent torsional, sorry, I got the figured out J, the torsional constant. I could have done a simple calculation and put in torsional springs and said the torsional springs represent the stiffness to ground. We talked about that on another kind of Tony talk earlier. So that's an alternative there. So boundary conditions tricky. Here's some discussion about over-constraining, under-constraining, and then this minimum constraint method, the plate balancing method, is a useful alternative. So that's kind of my thesis this week. I'd be very interested to see what the reactions to that are. And at this point, I'm going to hand over to David to tell us about what's happening next. And thanks everybody for watching.
Fantastic. Thank you very much, Tony. But before we close up, we've obviously got time for questions. So hopefully you can see all the questions that have come in there, Tony.
Yes, I can. The first set of questions, as I probably expect by now, is coming from Ivor. Thanks, Ivor. Nice to see you again. Ivor says, for the scuba tank conundrum, why not use average displacements equal naught and average rotations naught added to the system? You know, Ivor, I'm not quite sure how you would do that. Wouldn't mind going offline with you, Ivor, there to explain what's going on, to understand what's going on. It might be something obvious I'm missing, but it looks intriguing. But I'm not kind of familiar with that particular technique. So you'd go on further and say, for the minimum constraint model, add a left load driven by the average position rotation equals naught to get a soft constrained model. The little note popped up to say that somebody uses a 2-2-2 method. Yeah, I had my little recipe was 3 degrees of freedom, 2 degrees of freedom, 1 degree of freedom. If you have the corresponding orthogonal sets, you can have 2 constraint, 2 constraint, 2 constraints at the 3 nodes. As long as you've got 6 constraints, getting rid of the 6 rigid body modes, any of one of those kind of variations will work. Continuing with Ivor's comments, the 3-2-1 method might give local stress different from the average displacement rotation method. And Ivor says the main disadvantage of the average method is it may make your model non-linear. This takes longer to solve. Yeah, I'm really not quite kind of getting that method there, Ivor, obviously. Oh, he says that the average method is the inertial relief method. Okay, it's a better, now we're there. So yes, inertial relief is an alternative to the 3-2-1 method. We've got a question from Taha, says, what is the 3-2-1 method? It's essentially that slide I went through, and on the curator video I kind of put that slide back up again. It's a way of putting in a minimum constraint set. 3-2-1, again, we're putting in translations at 3 nodes. We put in 3 translations, 2 translations, 1 translation. The idea is that we don't lock in any strains, so any motion is possible. The analogy is rather like what we call a minimum jigging method. If you're building something up in a jig, let's say you've got a hard, stiff jig in the factory floor, you start to either weld or fabricate something in that jig. And what you can do is you can be putting strains into the assembly. So when you take that component out of the jig, it springs on you. It kind of goes ping. It goes into the shape it wants to go. To avoid that, there's a technique called minimum jig, which allows, or minimum fixture, which allows development allows that component to expand, contract, whatever you're doing with fabrication. So when you take it out of that jig, there's no surprises. So it's analogous to that minimum jigging type of technique. Gregory says, what's the difference between using inertial relief and weak springs? If we get it right, then we could pick points where instead of doing hard to ground, my 6 degrees of freedom, we could connect weak springs to ground. You've still got to connect them to ground. So that way, that would be one approach. But I think what happens is you're trying to pick weak springs to stop rigid body motion, so that, and again, there are techniques where the system can actually apply weak springs. What it's trying to do is to kind of give you it's almost like a mattress, to say, here's a mattress which is very soft, it's distributed throughout. So my outer balance force, instead of reacting hard at a single point, is reacted by a sort of set of distributed springs, rather like a mattress. Think of something sitting on a mattress. I push a force into it. I want to get avoid rigid body motion. So like putting the scuba tank, I guess, like on a mattress. Then the scuba tank can be pressurized. The mattress is distributed those reaction points. It can work. It's often used as a system fix-up. I don't like it because it can introduce load paths through the weak springs, which do strange things, and it doesn't really get rid of rigid body motion. So it's not a technique I actually like to do. In nonlinear, I will apply system springs, particularly to once if I've got a bearing pin coming into a bearing housing, and the nonlinear static analysis is a nearly rigid body motion, it hasn't developed load paths, then I will use specific grounding springs, very weak springs, to actually stabilize that. For example, spinning of bolts is fairly common. The bolts want to spin around in a nonlinear analysis. I can actually apply a torsional spring to ground. So it's a slightly subtle difference in there. Used as an alternative to inertial relief, I don't like it, but using specific weak springs to ground where I know what I'm doing, then that's a valid use. Ricardo says, in the case of the Conrod, acceleration in this field is given by the combination effects of the translational acceleration and the rotational velocity of the Conrod. I think the inertial relief can't describe that. Am I right? Not quite. I did a whole project on the actual inertial loading in a Conrod, and it is fiercely complicated. I've just taken one term out, which is the effective linear acceleration due to the centrifugal term. We also have the rotational acceleration term, and so on. The inertial relief will work because I can define, as well as that a linear acceleration, I can apply a rotational acceleration. And it took me about 3 weeks to figure out the inertia state of a Conrod as we go through the power cycle. So we can apply rotational velocity, rotational accelerations. Anything we want to apply is going to give us an outer balance. So we're not limited to just those translational accelerations. And then basically inertial relief will work in that case. If we've got a rotational acceleration, it will figure that out. So it will work there in that particular case. That explains why you get bending loads in a Conrod, for example. You'd think the Conrod is always going to be axial loads reacted by the piston and the crank, or the big end or the little end. It's those rotational accelerations and other terms which give the bending that's going to be occurring in the Conrod. So I agree with you, Ricardo. It's a much more complicated load path. Set of loads. I've simplified it greatly, but inertial relief could actually deal with all of those, as could the 3-2-1 method in there. For the rotational loads, it's best to use an Ivor says, for the rotational loads, it's best to use an FEM tool, applying a rotational loads on top of the other boundary conditions, gravity loads. Yeah, I agree with you. The unknowns, you've got the free body diagram, you've got your rotational accelerations. Just apply those directly and let the FE analysis figure out the distributed body loads is a good way to do. Tim says, how do we know when it's over constraint? I'm afraid it's really engineering judgment. We've got to look at something like my beam with the supported ends, the channel sections, and it's really a judgment call as to say whether we think this should be fully built in, should be simply supported, or somewhere in the middle there. And I think that's why I say it is really the most difficult thing to do, Tim, because, in other words, applying boundary conditions, because what is the real world doing? If we constrain, for example, one surface contacting another surface, we say let's constrain that to ground. We're supergluing that contacting surface to ground. If we apply the reaction force as a soft reaction force back again, then we are basically not constraining it. Maybe there's some guidance, there's some mutual interaction there, in which case we should perhaps do a nonlinear contact in there. But it becomes it's a difficult area. I can't really answer the question, Tim, other than using kind of like engineering judgment on that one. Christopher asks, what are your thoughts on globally applied soft springs? I kind of mentioned that before. I really don't like to do that because I don't know what the system's doing. It's like this mattress, this nice comfortable mattress, which is taking out rigid body motion by out of balance forces, if you like, by putting a nice distributed reaction throughout rather than a harsh local reaction. But it could be fixing up a problem in a way that's not physically meaningful. So I don't like to use that method automatically. Chris says, what's the best way to attach plates to solids? A couple of different ways there. What we can do is to actually overlap the plate onto the solid. The extra stiffness associated with that extra little region of plate is very small, and then we can bond them together. We can actually, if we've got the same nodal positions, we could use coincident nodes. We can zip the nodes up. We're assuming we're forcing continuity through bending continuity of the joint, then, but kind of essentially splining the plate to the solid through a line of nodes. So it's rather like a splining type of effect. There are special connectors which are basically going to use multi-point constraints. What they say is that the plate with all 6 degrees of freedom sees the solid, picks differential translations, and writes multi-point constraints between them. There are some special connectors to do that. So there's a bunch of different ways to do that. Anatoly says, thanks for the presentation. is it possible to eliminate rigid body translation in general case by fixing the center of mass? In the case of balanced loads, center of mass doesn't move. It doesn't move, but you can develop, for a redundant structure, multiple load paths. You may force the load path incorrectly through. If we take a simple example, like my favorite 2 men on a rope, I could take the rope and I could say, well, the center of mass is the middle of the rope there. Let's constrain that to ground, and then we've got the force coming from the right-hand side, force coming from the left-hand side. They're reacting in the middle. So sometimes that will work. It's a sort of like a variant on the 3-2-1 method, but instead of using the center of mass, well, in fact, if we use the center of mass and we've actually got plate elements, the plate element, one grid point can have 6 degrees of freedom. So we can actually, instead of the 3-2-1 method, we can have like the 6 method. So I guess that would eliminate all rigid body modes at a datum point, and that you might as well use the center of mass there. Unfortunately, for solids, we can't do that because we've only got the translational degrees of freedom. So then we have to spread the 6 points around 6 degrees of freedom to a set of nodes there. Colin makes the point, transient dynamic analysis incorporates inertial forces automatically. The inertial constraint approach appears to be a simplification to analysis of a dynamic case statically. Can you comment on that? It's not. It is using Newton's second law. It's saying force equals mass times acceleration. So it's actually not doing a dynamic analysis. What it's saying is force equals mass times acceleration for the outer balance forces. How do I develop those static forces to balance? I'm going to actually develop a set of distributed inertial forces. So we don't end up with the dynamics problem. We end up with a static problem. It becomes like a pseudo dynamic problem. Could we do the same thing in dynamic analysis? Yeah, we could do the same thing in a dynamic analysis, but it would just be a rather expensive way to do it. And also we'd have the problem that any load we apply dynamically just comes in with a bang. So we'd have to ramp the loads up gently. So yes, there would be an analogy to do it in a transient dynamic, but it would be a real pain to do it because we want to get back to a steady state equivalent static condition. Peter asks, on slide 16, do you need to split the load 50-50? I don't remember what slide 16 is, so let's nip back there. Do you need to split the load 50-50 before applying to the crank? Not quite sure what you mean there. I'm assuming that I've done a hand calculation to say this is without inertia. So in that particular case, let's say it's just the piston mass being flung out, let's say for the exhaust stroke. So we've just got the piston mass is applying the load here, and let's say that was whatever we said. I think it was like 5,000 pound, and then that's reacted by 5,000 pounds here. So it's just going to be P here reacted by P here. So we wouldn't want to split that 50-50. So I'm not quite sure where that's coming from there. Again, if you want to send me a supplementary email, whatever, I'm very happy to do that. Now, David makes a comment. He's telling students something. No, do I see the follow-up? Oh, there we go. David says, 2 things I always tell students. 1, results of the constraints are always incorrect. Analyze the assembly and only constrain the parts that you're not interested in. Yeah, that's a good idea. It's basically whenever we take a component like this out, like the Conrod we're showing here, and we constrain it, by definition, those are incorrect. It's going to be a more subtle load path through, and it is going to be a distributed reaction, not a constraint to ground. So I think what you're saying there, David, is that let's put the next component in, model that, probably contacts between those, and then somewhere to ground, like the I-beam and the cross members. There I put the cross members in and constrain the end of the cross members, which I think is exactly what you're saying there. The only trouble with that, David, is that we end up Sometimes it's like the knee bone's connected to the thigh bone and so on. We ended up modeling a lot of assembly to get to that point. I've come into big problems there with like US Navy DDAM analysis, where we're just looking at local deck regions, looking at shock loading. We want to basically look at normal modes analysis of that region, then do a shock spectral analysis on it. We're not sure of the boundary conditions there. We model the next piece of deck and so on. We actually had a case about 15 years ago where prime contractors were basically modeling like half the ship because of that, exactly that point. Let's connect that deck to that deck to that deck. We had huge models with like asking for 5,000 modes. So it's a good idea, but I think you must be careful not to obviously to go too far in that. But generally, yes, that's another way of doing it, is to actually model the surrounding structure in there. Steve Fisher makes a comment. When applying the inertial relief, you can specify where the inertia is calculated by, otherwise it does it at the 0 coordinate position. What is the benefit of specifying the center of gravity? I'm not too familiar with that technique. As I mentioned, the inertial relief method is a little bit subtle, how you're actually going to eliminate the rigid body modes. You can define those, as I kind of showed an analogy there, like with a 3-2-1 method, or you can allow the system to do it for you. I think I had a little picture in there to show it. This is the points I'm going to support the inertial relief, which is essentially not reaction points, but eliminating rigid body modes. It gets a bit subtle, and I'm afraid I just don't have that much. I've done it in the past, but I've kind of forgotten the subtleties associated with that, Steve, I must admit. So again, maybe we can kind of talk about that offline, and you can kind of remind me of the subtleties in there. Ivan makes the comment, I believe the inertial relief is basically adding 6 lines or extra degrees of freedom to the matrices by forming average U1, 2, 3 equals 0 and average rotations, and solving the rigid body modes as a basic least squares minimization method. You remove the RBMs. Yes, it's doing something like that. It's basically sometimes it is figuring out the best way to augment or partition that matrix so you can actually solve it. So it's not kind of like a physical analogy where we actually putting reactions in or constraints reacting to ground. It is actually partitioning out or enabling that matrix to be solved. The mathematics behind it, I did dive into it sort of like 10, 12 years ago, and again it comes back to Steve's point. I've skipped the mathematics behind there. There are some implications in there, which is why I actually prefer to use a user-defined support positions. Think about the kind of the 3-2-1 type approach, and have a kinematically feasible way of constraining out those rigid body modes. Anatoly asks, for the unconstrained case, the resulting system of linear equations with a stiffness matrix has an infinite number of solutions underdetermined. Can we say that we're looking for one with a minimal norm? That's kind of part of it. You're actually, in the inertial relief system, you're actually, I really need to dive into the mathematics. I know I have a friend who's very good at this, so I'm going to call a friend when we kind of finished here and say, remind me about the mathematics associated with the inertial relief. It's not trivial, that's for sure. It is not an analogy of just the 3-2-1 constraint method. Oh, David mentions 3 symmetry planes are your friend. Absolutely. I could take the Conrod here and say there's a symmetry plane through the middle. There's a symmetry plane through here. And I'm going to see a symmetry plane down the middle. What you've done then with the symmetry boundary conditions, which are constraints, is you've actually put in a fully constrained model, but those constraints are physically meaningful. Those constraints become the cut face constraints, stopping movement across the plane. So if you've got something which you can, and unfortunately we can't apply a symmetry plane down the middle here, we can only get 2 planes of symmetry in here, so we're still stuck with 1 constraint. But then we can just, the 3-2-1 method, as you apply one boundary condition, one symmetry condition, it becomes a 2-1 method. As you apply the second constraint, it becomes the 1 method, the symmetry plane. By 3 symmetry planes, it becomes the 0 method. You've actually constrained all rigid body motion. So again, symmetry planes are great if your structure lends itself to it. Here I can get 2 symmetry planes, and I've just got 1 constraint left to work with. So sometimes it can be very, very useful. Steve says, reading the manual, the ability to specify the grid for inertial relief to occur seems to have been removed. The code has obviously got better. Than the system I used, I was able to define it or have it automatic. So I still like defining it manually. So again, I think there could be a good offline discussion in here. Okay, so a slight correction there. You define the point of the mass by another parameter. Param grid point is basically the point you're going to calculate the inertia properties about, and it's actually stealing that to say that's the point you're going to apply the constraint to. So there is still a manual method in there. Well, I think that's a good set of questions there, David. A pretty good run through. So I think I'll just go back to the marketing slide, and we'll finish on there. So I'd like to thank everybody for all those questions. It's great. Thank you very much for everybody that tuned in. And I'll hand over to David to wrap up the session for us now.
Thanks very much, Tony, and thank you to everyone, as Tony says, for your questions. It's been great to see those coming in today. So that's it for today's session. We would hope to see you again next time, September the 4th, where Tony will be looking at dynamic response types. But for now, that's us, all from us just now. We hope you have a great weekend, and we hope to see you at another Talking Shop or NAFEMS event very soon. Goodbye for now.
Thanks, everybody. Goodbye.